In the final part of today's lecture, we'll first study the problem of off-policy evaluation, where, where the goal is to find the return of a given policy pi without running that policy in the environment. So rather than trying to find an optimal policy, which offline RL tries to do, we want to estimate the value function of the policy or estimate the performance or return of the policy pi given the fixed static data set D. And what this will help us with is that this will help us making, for instance, comparator decisions. In that, if the value function of a policy pi1 is greater than policy pi2, then maybe the policy pi1 is better or high performing than policy pi2. As a practical example of where this could be useful, there's this domain of healthcare where we could compare the effectiveness of different treatment policies or treatment plans using offline data and use that to decide which treatment plan should be executed for a particular patient. From an offline RL perspective, the use of OPE is in the problem of model selection, where we are interested in selecting which policy is good. So imagine we run an offline RL algorithm, we store all the policy checkpoints that we observe during training, and we then try to use an OPE style method to select which of those policies should be the policy to finally deploy in the environment. Why do we need model selection in offline RL? Why can't we just pick the last solution and be happy with it? So similar to supervised learning methods, excessive training on the same offline dataset can lead to poor solutions. For instance, the method could overfit, or there could be other sort of optimization difficulties that can happen. On the other hand, if we can rank these solutions using OPE reliably, we can end up choosing the policy that attains the best performance, and hence our overall offline RL algorithm output would be quite good. So in that sense, model selection can sort of supplement offline RL methods, and offline RL methods may not have to deal with various issues pertaining to fixed data set training. So we'll not cover OPE methods in any detail at all, but I just wanted to give a quick overview of what kind of methods people have used for OPE. And this list is by no means exhaustive, and there's a lot of research in off-policy evaluation, a lot of exciting works in this area, which I would encourage you to check out. The list is a list of these references is provided in the reading list at the end of this lecture. So one of the most classic approaches towards the problem of off-policy evaluation is this family of methods based on importance sampling. So this is again something we have looked at in this lecture as well as in a prior lecture, where we could estimate the return of a particular policy pi using data from a different policy pi beta by importance sampling. And we also looked at how this could be estimated in an offline way by just using a static data set, by approximating this expectation in terms of the samples, and how this has high variance, and there are some fixes like doubly robust estimators to fix this. There's another class of interesting methods that has recently been becoming very popular. It's based on this high-level idea called marginalized importance sampling. So turns out that you can, or I guess you already have covered this, you can rewrite the RL objective or the return of a policy pi theta in terms of the average value of the reward under the marginal state distribution of the policy. So expected reward under S and A drawn from d pi of S comma A. And with this, you can also perform importance sampling on this representation of the RL objective. And if we do that, we end up getting a ratio that is the ratio between t pi of SA, which is the marginal state distribution of a state action pair SA under the policy pi, divided by the marginal state action distribution under the dataset, which you can estimate by fitting a generative model or something. There's been a lot of work to approximate this ratio or estimate this ratio using many sort of techniques, and they have a lot of trade-offs here and there. But it's a lot of exciting there's been a lot of exciting recent work in this line of thinking. Finally, you could also do something other than importance sampling, which depends on using a Q function to directly evaluate the return of a policy pi. So unlike actor-critic methods, where you would estimate the Q value for a policy or for the actor policy and update the actor policy based on the Q function, here you would try to estimate the Q function for a fixed policy pi that is given to you because you're trying to evaluate it. A lot of prior work is there on this, and you should check out a lot of the references. However, OPE has turned out to be somewhat challenging for with deep neural network policies, especially with scenarios where your data coverage is somewhat narrow, because in that cases, a lot of these methods may not end up working, and they might suffer from similar issues such as distributional shift, and so it's a bit unclear how to really get them to work. That's it. Okay, so that was the OPE bit. Now we move on to the second part of this of this final module, where we discuss how we should evaluate offline RL methods. So, what's our main motivation for offline RL, or what's sort of our ultimate goal with offline RL? So, our goal is to be able to use real data, which is collected from various sources, such as human demonstrations, runs of hard-coded policies, maybe even prior runs of RL agents, etc., to be able to train good policies via purely static or offline training. So we can directly train on real data, right? I mean, in a sense that there's a lot of real data available, we can as well train on it. So we can train on a lot of driving data or robotics data or something else. But one of the primary issues with training in reality is that we don't know how to test the policy in the real world. Meaning that when we are prototyping a method, it's unclear how you would, or it's very sort of unrealistic even how you would want to, or how you would evaluate a policy generated out of RL in the real world, because that policy might actually end up being bad. So therefore, we want some kind of benchmarks that have the right properties or have the right motivation in them, but they also give us simulators where we can actually test out our policies. So what properties such a benchmark for offline RL have? So first, it should be realistic. It should mimic the properties that we would want to see in the real world. And secondly, it should provide us with a method to compare different algorithms in a standardized way. And this evaluation scheme ideally should be a real evaluation. So it should be an evaluation where you actually execute a policy in the environment, meaning that you have a simulator to the environment. So in some of the work that we have done here at Berkeley, we ended up designing a benchmark for offline RL. So before going into the benchmark, let's look at what prior evaluation has done. So most of the methods for offline RL have so far been evaluated using data collected from RL policies, as we have also seen in the past, like data collected from a partially trained actor-critic policy or something like that, or even like replay buffers of DQN agents. And these scenarios tend to be substantially simpler than real-world scenarios. Why is this the case? So very intuitively, in a replay buffer or in an RL policy, you're precisely seeing those transitions which were needed for the same for an instance of the same algorithm or a very similar algorithm to learn. So in a sense, you are kind of probably doing the hard part. You're already giving away the offline RL method, the hard part, which is that the data was collected from a similar RL algorithm in it. So what we would want to do here, what we wanted to do here was to build a benchmark that does not have these properties, but rather it has some other properties that we expect to observe in the real world. For instance, we expect to observe non-representable behavior policies, meaning that the behavior policy is not even a Markovian distribution. It's not even representable in your function class. Depends on some privileged information, something like that. Where you expect to see narrow distribution, so your coverage is very limited towards a small region of the state action space. Where you expect to see undirected or multitask behavior, meaning that the policy is not trying to, or the behavior policy is not trying to optimize the reward function that the offline RL problem is supposed to optimize. And then you also want visual perception, because images can be extremely hard, as well as human demonstrations, because the set of actions that humans take can be sort of somewhat harder to model, because the human might take very deterministic actions, or they might do mental planning in their mind and take certain actions which might be hard for an RL algorithm to infer exactly what to do out of. So in order to do this, what the D4RL benchmark consists of tasks which satisfy these properties, such as the ant maze or the point maze tasks, which consists of behavior policies that are not representable in the function class that is chosen during training. Then there are tasks with extremely narrow distributions, such as the robotic hand task that we saw earlier with the CQL results, where the data consists of a very covers a very thin manifold in the space of all state action pairs. Then the Franca or the kitchen task, which is on a Franca robot, which we saw earlier, it consists of a lot of undirected or multitask behavior that is not even relevant for solving the task at test time, or not relevant for solving the offline RL problem that you are seeing, as well as tasks pertaining to driving on the Carla simulator and human demonstrations as well. And this benchmark comes with standardized metrics. So if you're considering doing offline RL or something like that for your project, you might want to check something like this out.